Fine, good. So, hello, last presentation. We have almost done it for this year. So, yes, I'm from the University of Göttingen, the group for software engineering for distributed systems. And this work is actually mostly done by my colleague Zaheed Ahmed, who was unfortunately not able to come here and share his ideas with you. So he's the expert on the topic. I'm going to try my best to communicate his ideas, but yeah, let's see how that goes. So we're going to be talking about mutants. It's a topic that kind of comes and goes over the years. Now, again, it's starting to enter a new hype cycle with AI and neural networks. Show of hands, who has heard or knows anything about mutation analysis or mutation testing? Not many. Okay, I'm gonna have to explain some things. So, yeah, let's have an overview of, let's just go ahead. Okay. Okay, we're going forward, good. So after a short introduction for the uninitiated on the topic of mutation testing and mutation analysis, I'm going to talk a little bit about challenges with mutations in the context of machine learning and how this is different from the traditional development paradigms that mutation has been previously used in, and which specific issues occur there. There seems to be some debate in the literature, so I'm going to touch upon that and try to maybe put forward an idea of how this kind of debates could potentially be resolved. Then we're going to look in particular on the subject of mutant selection criteria and why that matters and what is out there and what we could do better going forward. So, mutation analysis, what is this about and why do we need it? Why should you care? So the idea of mutation analysis or also mutation testing is that you have your piece of code, your software, function, whatever, and you can mutate it. You can change little parts of that. You can change, for example, comparison operators, you can change mathematical expressions, let's say. Plus or minus, larger than to smaller than, and so on. And you create, by applying this kind of transformations, a set of so-called mutants. Now, why do you need mutants? That's the second part. And this is basically, you want to know how good your tests are in detecting defects. And one way to assess that is to create artificial defects or something that resembles artificial defects. Run your tests against that and see if your tests are able to detect mutants, in which sense we say then mutants have been killed. So some of the mutants will be detected, hopefully, if your tests are good. But there might be also some that survive that are not detected, and there's different reasons why might that happen. One of them being that some mutants might be equivalent. So they might not actually manifest in difference of behavior that can be detected by tests, and there is also other issues there as well. So that's kind of mutation testing or mutation analysis in a nutshell. So the goal here is to see, okay, are my tests good enough? Can they detect different types of errors? And yeah, the key motivation is obviously the assumption that those mutations are somehow similar to actual faults that people actually do while they program, while they develop software. So it's kind of one of the underlying assumptions that programmers are kind of competent. They approximate the solution, but they might make some little mistakes. They don't do things completely incorrectly. So that's kind of the idea. And then there's, of course, some hurdles. This process can be quite computationally intensive. So first and foremost, you have to generate potentially large set of mutations. And then you have to evaluate those. So you have to run the test, you have to compile the code, you have to perhaps process things a little bit to optimize the evaluation. So this can be computationally intensive and time demanding. Now, what about mutation and deep learning? So the core idea is, as I said, to try to assess how good the tests are. In machine learning, the tests come in the form of test data. You have the test data and you want to see how good is your model to provide the expected results. But that's just one way. In the past years, people have been quite creative in coming up with different ideas how to apply mutation analysis. This could, for example, be used to prioritize which input data you want to label. If you have incoming data, maybe you want to optimize that process a little bit. There's a bunch of literature on that topic. Then it could also be used to assess the model's robustness, so going beyond the assessment of the test data. You might also want to use that process to generate so-called adversarial samples, which kind of seek to highlight some underlying issues in the model or maybe even in the data. It could be used also for test data generation and for fault localization in deep learning systems. So with that in mind, there's been different applications for mutation analysis, but there is not much of an agreement of how to do that. And so that's where we kind of try to put some ideas to figure out how mutant generation and mutant selection can be performed in an adequate way to have useful mutants and to improve the process, because as I said, there is a bit of a debate, which is where I'm going to come to in a little bit. So just again, coming back to classical development. So the process is typically kind of straightforward. We have the developers that work on a program, on the code. This is being compiled maybe multiple times in different representations, and then you have the executable code. And from a process standpoint, we kind of assume, okay, mistakes are really happening in the beginning of that change. So when you code, you might misunderstand something or mistype something, and then bugs might emerge in your code. Now, when we apply mutation to try to simulate such kind of faults, obviously, we try to introduce those faults in the source, in the program. This is the most kind of straightforward way. Of course, this implies then that you have to repeat the process afterwards. And since this process is generally deterministic and straightforward and way well understood, to optimize the process, of course, over time, people have also come up with ways to apply mutation operators in the intermediate representation so that you can skip some of the steps along the process, because you can map between, for example, the binary code and the corresponding source code so that you can do exactly the same kind of mutations, and you don't just shift bits back and forth, because this can create some unexpected noise. So this is kind of one fundamental difference when it comes to machine learning. So this is the classic approach. Now for machine learning development, things look slightly differently. Obviously, we don't necessarily write the code for the model directly, but rather we might calibrate or configure a training program. And then we feed some training data, which we also have to prepare as part of the development process. This then goes into the training, and this gives us the trained model. So again, from a process standpoint, mistakes tend to happen in the beginning here. So we might not prepare the data adequately. We might have mistakes in the labeling. We might have incorrect data points, like some noise and so on. And we might also misconfigure our training programs. So we might choose the wrong algorithm, enter the wrong parameters, or have some other issues there. Now, the machine learning community has been trying to also come up with ways to apply mutation testing in this context, and the obvious ways, of course, also to start at the source here, as the training data and the training program. And because the training can be also very time consuming, in analogy with the classical process where you modify also the compiled artifacts, there have been also some proposals to actually just work on the trained model. Problem there is that this process is not necessarily deterministic. Most of the time it isn't. And also this part is here not very well understood. So what do you modify here? How does that relate to actual problems that people can introduce? Is also not very clear at this point. There is also other conceptual perspectives here that kind of think of the process from different ways of looking at it. So I'm going to come to that in a bit. So yeah, what are the challenges? Well, what do we mutate? As I kind of indicated, the different points of view, there's a bit of a debate there. So do we work just with the training data? Do we work with the training program? Do we consider the trained model, or is it completely out of context here? So that's one aspect. And the other aspect is once we start to actually generate mutants, how do we determine which ones of them are useful? So as I suggested, some of them could be equivalent, some of them could be trivial. So they could make such a big difference in the behavior that any test would detect them, or just the test wouldn't even run because the problem is so big. So we want to have mutants that are similar to actual mistakes. 5 minutes, okay, I have to hurry up. Good, it's a short paper, so a short presentation to go with it. Right, so there's been two different categories, two different schools of thought, if you want, in the literature. One is focusing on the source level and arguing that that's the only place to do mutations because that's where mistakes would happen. And the other school of thought is looking at the model and insisting that that's actually the right place to do that. Why so? Well, for example, some authors have thought of this as a kind of test-driven development scenario, where you have the data, which is your tests, and then you feed that into the model during the training. And if the model fails in the beginning, you adjust something, then you train it again, you adjust something more, and you eventually approximate a model that is able to pass training data, so to say. So yeah, from this point of view, authors have claimed that, well, if you start to introduce faults in the training data, you're actually introducing faults in the test suite, and that's not how mutation testing is supposed to work. So from their point of view, only the model level mutations actually make sense. That's one way to look at that. From the other point of view, the argument is that test data is responsible fundamentally for what the model learns. So this is actually kind of the code for machine learning systems. So mutating data is like mutating code. And furthermore, the argument is, as I said, that it's not trivial to determine which mutations in the model translate to which mutations in, or which mistakes in the training data and the training program. And therefore, just randomly shifting weights in the model, it might look quite artificial and not based on reality. So in comparison, in traditional approach, this process is deterministic. So if you modify something in the binary representation, it can be traced back to actual mistakes in the code. So the proposed perspective is 5 minutes.
No, okay.
We have basically the process looks like this. We have different levels of refinement of the data as part of determining suitable data to meet the requirements for the systems. It's a big part of machine learning systems. And then you have a more specification, which indicates which algorithm is to be used and so on and so forth. And this gives us our model for training. Now, this picture might seem somewhat familiar to some of you, perhaps. Well, this looks very much like formal methods, right? So we have requirements and we have refinement of the specification on multiple stages. And eventually we have perhaps formal enough specification that can be fed into a code generator and give us the actual running software. So this, we're trying to kind of reason by analogy here. There is no debugging for those of you that have noticed, because code generators are perfect. But yeah, that's a topic for another talk. So going back, we argue that actually both, looking from this point of view, both source and model level mutations make sense, unlike what some authors have claimed in the literature, because they all are kind of contributing into the final product. And we also have a definition of an MO mutant, which includes all these different components, and the goal there is to simulate a real fault. So this is kind of the baseline here. So how do we define what is an acceptable mutation? And the next topic is really how to determine what are the useful mutants. So we want to have the good mutants and not the bad ones and not the ugly ones either. So a reference to cartoons from the 80s. For those of you who have grown up with that. So yes, there is different implications. So first and foremost, when we're talking to classical development mutations, mutations are kind of well defined. You change just one mathematical operator, comparison operator, you name it, but that's kind of one thing that you change. In deep learning, mutation operators are parametric. You don't just change one item in the training data, but you have maybe some criteria like, I don't know, change 5% of the data, shift 5% from one label to the other, and so on. So one operator can actually generate many different mutants, and those can also be, to some extent, also trivial. You might have substantial changes in behavior that you might want to exclude because they're not really useful. The other part is that some of them could also be equivalent. There might be not a large enough change. And the goal is, as I said, to try to be actually making small mistakes that are still close to the correct behavior, so to say. And the challenge here is that it's difficult to determine upfront which configuration for your mutation operators actually leads to which type of result. So this is something that we think should be looked at. And then the other part is there is already different criteria that have been proposed in the literature that might be useful to determine which are the good mutants, but they need to be evaluated a little bit more in detail. For example, the most basic approach is anything that doesn't crush is good enough. So that's the obvious starting point. Another point is to look at the error rate. So how far are we deviating? So how much of the test data is actually leading to failures? And this is kind of next stage. Then we have another stage, which is looking at different performance characteristics and trying to stay within certain boundaries to determine, okay, these are mutants that are different, but not that different that they're obvious to detect. And then the last approach is to have a set of different criteria that try to score the mutants on different aspects, how trivial they are, how easy to kill or not they are, and whether they are subsumed into other mutants. So yes, we did a bit of a comparison, and you can see here kind of the evolution over time. And yeah, the more sophisticated approaches, they can obviously address different types of undesirable mutants that we want to detect. So one of the key challenges here is that we're talking about semantic changes. So all these mutants that we contemplate in machine learning, they have semantic implication in that we are detecting them by looking at the output. In contrast, in the classical paradigm, we're talking about syntactic changes. So valid mutants are mostly defined based on that. Then there is different notions of simple and complex mutants that also need to be reevaluated in the context of machine learning, and also the different fundamental hypothesis mutation testing might need to be reevaluated in this context. So this is where we go also to our ways forward. So one aspect is, as I mentioned, there is different criteria, and we need to have a bit larger scale, more systematic evaluation to see which of those criteria are actually suitable for the different purposes. Another aspect is to try to map mistakes on the source level to mistakes on the target level to try to see, okay, can we learn dependencies between the different mistakes that can happen on the source level and how they manifest in the model level. So to have a kind of more traceable relationships there. And then to reevaluate this fundamental hypothesis. If you have questions what they are, I can explain afterwards, but I'm struggling a little bit with the time here. So yes, these are two different hypotheses that can we make, what does it mean to have behavior similar to the original? And is there a dependence between simple and complex mistakes, so to say? So yeah, that's all from me very quickly. I thought I would be too quick, but apparently I was too slow. So we talked about different challenges in machine learning mutants, our proposed perspective, different challenges about mutation selection criteria, how they could be addressed, and different ways forward that we see as next step for this field of research and that we would work on, but we also encourage others to take part in. So that's all. There's some references there if you want to follow up on that, more in the paper if you're interested. Thank you all, and open for questions now.